Now I'm recording. So just as a reminder, just to start off the video here, I do have a guide for drawing lens diagrams in with your videos, and we're reviewing our mirrors. So we're doing that law of reflection in order to get it. So the images that are formed are actually they intersect where they appear to originate. So that's what we were showing by doing our ray diagrams before. So we did a flat mirror. You have a video, or you have a video and a written and a talked over item about doing what size of a flat mirror that you have to see your entire body. So you do have that. And remember that magnification is the image height divided by the object height. If it's negative, it's going to be flipped. It will be inverted. If it's positive, it's going to be upright, just like this one is in there. And magnification does not always mean it gets bigger. If I have a magnification that's less than 1, my object is smaller. We're going to call this the principal axis so that we have that. And I can use 2 rays in order to define where my image is. We're going to see that again in lenses, that you'll have that 2 rays where the image is. So the image is going to appear with a flat mirror. It's going to appear as far behind as you are in front of the mirror. The image on a flat mirror is usually unmagnified. If you did a magnification, you don't have a truly flat mirror. You may have distortion. And if you think of makeup mirrors or corner mirrors or things that are curved, you do get that nice curve. And remember that your side mirrors, there's usually a disclaimer on your side mirror that says that objects are closer than they appear because you don't truly have a flat mirror. So that's why they actually tell you that on your side mirrors on your car, because your object, because if I have a truly flat mirror, we judge that distance, but we can't judge that distance if we have some kind of curvature, which we typically do with our side mirrors. So remember, mirrors, if I'm seeing the image appears to be behind the mirror, that's going to be a virtual image, and we see that virtual image come about because there is no true light there. So when we start distorting our mirrors, giving things like being able to do day settings or night settings, you get that change in your reflection. We get the incident ray. It's going to come in a little differently, and we're not going to get the full effect of the light. So after we did our flat mirrors, we started talking about curved mirrors. And we still have our principal axis. Our mirror is going to be defined by this radius of curvature. That's where we have our center of curvature and our radius. And remember, our focus is going to be 1/2 of our radius. So we'll get our focus. If I'm on this side of the mirror, this is going to be what we call a concave mirror. If I'm on this side of the mirror, that's my convex mirror. And we can use our ray diagrams to predict where the image is going to be. And we use those double rays just like we have before. We talked about the fact that we can have rays coming from multiple places. We can have light reflected different ways as well. So I can get dispersion, and we can see that piece. So this was our big diagram that we worked with last week. So here's my object. We use going through the radius of curvature to the other. That's going to form one of our rays. Then we have from the top to our principal axis. And then we use our angle of reflection, and we have it bounce, and then we'll ultimately get our image. If my object is outside of the radius of curvature on a concave mirror, which is a converging mirror, remember we talked about converging and diverging. convex mirrors are going to be diverging. We could show how our magnification came about by using our distances. We could show our focus. We have our mirror equation, and we have our magnification equation. Now, if I move my object inside the radius of curvature, I'm going to get a little bit of a different image. And we showed those 3 ray diagrams to be able to see if I have a convex or a concave, if I have my object outside or inside my radius of curvature. Then we talked about, well, what happens if I have parallel rays of light coming from a great big distance away, where we get that focus. And so we could rewrite our mirror equation to actually include focus. So that was one of the things that we did last week. Here's our convex mirror. These are diverging mirrors. We're still going to get a virtual image. This one is going to be upright because I'm getting that from out there, but I'm still using my ray diagram through my radius of curvature. And I'm using my ray diagram to where I can go through my focus, and we can get those images there. So that should help everybody. We also talked about having these charts available when you're doing these problems, because this helps keep track of what whether my number should be positive or negative. So when you're doing your homework, you want to double check these sign conventions, because that's really going to help you solve your problems. And that's going to really help you out there. And then we did a variety of ray diagrams. So we showed I can do 3 rays. 1 is a check. So we did the 2 before. You can go through the focus. That go through the radius of curvature, go through the focus, use my reflection, and we can come back and get those as well. And then this was the other one when I had if I do my object inside the focus, I'm going to get a virtual image, whereas this image here is a real image because it's in front of the mirror. This one's a real image, whereas this one is going to be a virtual image, so that you can work with that. And then we did our other diagrams as well. So you have those there. And we just now talked about our objects are closer than they appear. So you do have that you have out there. Now, when we start moving into thin lenses, and thin lenses are really slick, we start talking about how we get images formed by refraction. So this is the classic paperweight problem. So most of you have gone on vacation and you go into the novelty store and there'll be a tarantula, or there'll be a penny, or there'll be a coin, or there'll be a rattlesnake head or something inside my glass that I have. Well, what happens to us is if we have this curve here, we're going to have to take into account our curvature. We're going to have to do that. But mostly we're going to have to account for the fact that my glass is a different index of refraction than the air. This could also be if I'm underwater. And if you've ever watched those nature programs and the bugs are trying to get, or the fish is trying to get the bug above water, or you've ever seen a little kid reach into a pool or a pond that has lots of goldfish, and they try to grab the goldfish and they can't, because the goldfish looks like it's someplace where the goldfish isn't. If you're in a tidal pool and you're dealing with touch in a tidal pool, you look down and you want to touch something and you think where that image is, it's not really there. So that's one of the things that we have to account for. We're going to use our same conventions. We're going to use our P's and Q's, where P is the distance between the object and the surface that we're dealing with. Q is the distance between the surface and wherever the image is. So we're still going to use those. We have something that looks like our mirror equation, where I have my radius of curvature, but I have to take into account my indexes of refraction. Now, remember what we said about refraction, because it's going to come into play with thin lenses. It's a little different when I've got a thick object, like my paperweight or my water or my pond. It's going to be very different. But if I have a thin lens, what we saw was if I had light pass through my kind of little square, it bent, but when it came back out, it bent back. And that's what we're going to use for our thin lenses. It's going to be really tricky when we deal with our thin lenses, because that we can kind of disregard those indexes of refraction when we're playing with our thin lenses. But here are our sign conventions. And again, I remind you, please go look at the paperweight problem. You have that example in your book. You also have, like I said, I've done it a couple of different ways in Blackboard. You have it as a talked through problem. And if you click on the colored material, it will actually talk you through each step. And then I think I also have a video of it as well. But you do have those sign conventions. Here's our flat object situation that I was talking about, where here's my object is really here, but this is where my object appears. So if I'm trying to grab the fish, this is where I end up trying to grab the fish, and that's not gonna work. So, and it's a virtual image, it's not really there. So you do get that. Now, we can do some interesting things. I don't know if you've ever seen any of this, but on certain atmospheric conditions, it looks like ships will be floating above the water and look like they'll be floating in midair. So if you've ever seen, somebody says this is a ghost ship, where it's up here and it's a ghost ship. It's not really a ghost ship. It's the refraction that's moving the image of the ship to some place that we don't normally expect it. And I have seen it happen. It's pretty cool when it does happen. You get it different places, and it kind of does really some weird things when you see the ships. But it's all related to the fact that you have a different index of refraction associated with your conditions in the atmosphere, and it will cause some strange things to occur. This is also why you get things like your heat effects or your mirages. That it explains a lot of those items where things look like they're being reflected or they're being in different places, and you can get a lot of interesting optical illusions, essentially. But it's an optical illusion that's based upon the fact that you're getting some different refraction that's occurring. So when we're dealing with thin lenses, you can usually tell what type of a lens it is by its shape. Okay, we talk about converging lenses, just like we had a converging mirror, and diverging lenses, just like we had a diverging mirror. These lenses that are in the top category. We call this bioconvex, where we have the curve here and the curve here. We have a bioconvex, we have a convex concave here, and then we have a plano convex. These are all going to be converging mirrors. One of the characteristics of a lens, one of the characteristics of a converging lens is that the middle is fatter than the ends. Okay, that's one way that you're going to be able to tell which one is a converging lens, because my middle is fatter than the end. Now, if I have something like this, where I have bioconcave or convex concave, but now I've got a real drastic piece here, and plano concave, here my ends are wider than my middle. And these are all going to be diverging lenses. Those are all going to be diverging lenses. So what happens with a converging lens? So if I have my parallel rays coming through, it's going to focus the light to a point. My diverging lens are going to bend the light away. So these are probably going to give us virtual images, whereas this one will probably give us a real image. So we have those items that are going back and forth. Now, just like we dealt with our mirrors, here's my object and here's my image. So when we draw our thin lens problems, you're going to draw a representation of your lens, and you can get away with a straight line. Okay? You can get away with a straight line. Now, this particular lens is a converging lens. Here's my object. I usually am told what the focal point of my lens is. So there's my focal point. So I can do these to scale. So if this is in centimeters, I'm going to put my object 6 centimeters away from my lens. I'm going to use this as a 3 centimeter focal length. So we're going to say our focal length is 3 centimeters. Now, when I put my object out here, I'm going to take my first ray, go through the principal axis, and draw a line. So I'm going to use these 2 points to form my line. All right, so there's my first one. That's my first ray. My second ray is going to be parallel to the principal axis. It'll come to that midpoint of my lens. And then I'm going to use this point and the focus to create my straight line. So I'm going to put in my straight line, and where they cross is where my image is going to appear. So this is a converging lens. So if I put a piece of paper here, I would get my image. It would show up on my piece of paper. So it's going to be a real image. It's inverted. So my magnification should come out to be negative. Okay, it should come out to be negative to tell me it's inverted, because I'm going to use my sign convention just like I used my sign convention for my mirrors. And I can actually draw this and predict based off of my drawing what my Q is going to be. They gave you P because that's how we started. They gave you F, so I can determine where my Q is going to be using my thin lens equation, which should appear right here. So here's my thin lens equation. It looks a lot like my thin mirror equation, or my mirror equation. I've got a similar table for my thin lens. If I'm in front of the lens, my P is going to be positive. If my Q is in front of the lens, it's going to be negative. And then here's my backlight. So this is my incident light, and this is my refracted light. Now, if I have a converging mirror, I'm going to use a positive for my focus. If I have if I'm using a converging lens, I'm going to have a positive for my focus. If I'm using a diverging lens, I'm going to have a negative for my focus. So it will work out as well. Now, if I'm making a lens, this is called the lens maker equation. This is how I'm going to determine what my focus is based on the different curvatures that I have for my thin lens. All right. This is gonna give me whether I have a convex, a concave, convex, or a plano one. This is my lens maker equation where I'm going to determine how to make my focus. So you do have that in there. So here's doing a ray diagram where I can go through my first focus. That's going to be related to this side. My second focus, which is related to that side. I can draw my lenses and I can work through that. And I'm going to use my same my third ray goes through that focus and then parallel to get it. So I have a check ray. So I do have a check ray. 2 rays will define where my image is. My third ray will give me that check. Okay. If I put my object inside the focus, I'm going to get some diverging things here, and my image will become a virtual image. So on your exam, you're going to have a thin lens problem, usually a thin lens problem with a converging lens, a thin lens problem with a diverging lens. You will have a mirror problem that you have to do. Just like what you're going to see in the homework, you've got all of those in there, and then you will have one double lens problem, and we'll talk about that double lens problem in just a second. So you have this situation where my object is inside that focus. Now, if I have a converging or diverging lens, this is what I'm going to get, and you can step through those rays to get there. Now, when I have a combination, okay, a combination of lenses, you take them one step at a time. So I will do lens 1 first. I draw my ray diagram and it gives me my image. This image now becomes the object for the second lens. Okay. My image becomes the object for the second lens. So you're doing it as a step 1, do the lens problem with lens 1. When you get to your image, the image is now the object, and then you can do your image, or you can do your lens problem again. Now, why do we do double lens problems or triple lens problems? You won't have to do anything more complex than a double lens problem in this class. But if you think about a microscope, you have the lens that's down at the bottom, and then you have at least the eyepiece lens. Sometimes you have a different lens in the microscope. Telescopes the same way. I have my eyepiece lens and I have the lens at the end of the telescope. Now I change that distance between the 2 lenses to get the image that I want. Same with your microscope. You're changing those distances in order to A, focus your image, and B, be able to magnify the image. So especially if you're dealing with a microscope, that's what you're trying to do, is you're trying to magnify the image. So that's why we have to worry about dealing with our combination of lenses, because those combinations of lenses give us our optical equipment so that we get that. Now, we can still have aberrations, just like we saw with our mirror. We can have aberrations where they don't quite come together. And if I'm diffracting light, so if I start with a white light and I get the reds and greens and spread them out, I will get those things spread out as well. And you can get spherical aberrations associated with your, just like you have with your mirrors. And then we talked about the color. This is the chromatic one that you will get. Okay, so this PowerPoint, at the end of it, you have your sign convention charts. So I've kind of pulled them together for you so that you do have those, so that you can walk through those pieces. And it shows the various ray diagrams. So if you want to print out something to have when you're working your homework, these summary slides are probably the best for having that right there as you're working your homework problem. You don't necessarily need this aberration topic, but these 4 slides where you have your sign convention charts plus your drawings to be able to see are really the best items to have for that. All right, so that's the material. Are there questions or things that anybody wants me to go back and clarify? I think they're fun. I like drawing them out because it's one of the few times that you can draw them out and do it graphically and it actually works. And you can verify your mathematics. It's really great. So this is one that you can go out and play with. Or if you have any other questions for me, please, again, I did send out, oh, I got a chat. Okay, the last, explanation's just a good observation. So try to explain it in terms of reflection and refraction if you can. Just also tell us, if you're seeing a rainbow, that you're getting that spread out on the dispersion. So there, you're gonna want to draw your pictures on your exam. You get at least a point just for drawing the picture. And just as a reminder, I'm looking for 10 images associated with the things out there, and I'm looking for 3 pinhole images. There are a couple of the ones that you won't necessarily have to draw a picture for, but when you're doing your lenses and your mirrors, you're going to want to do a picture. Also, just as another reminder, some of you I have sent messages to. So please look at your messages, and I do have in the announcement the list of the stuff that's due this week. All righty, guys, I'll see you tomorrow if I don't have any other questions.
Can you explain to me how to do a pinhole picture? I'm not understanding exactly how to grasp or
Okay.
the concept.
Okay, so if you see a pinhole camera, say make a pinhole camera out of a shoebox. All
Okay.
right. So you've got your pinhole that's going to create the image on the back wall of your shoebox.
Okay.
Or another one is a Pringles can. A lot of people have used Pringles cans. Okay. You can do with a paper tube, just a paper tube. You can put a piece of paper on there, but a paper tube works really well. So for example, just to get a pinhole, take the toilet paper tube or a paper towel tube. On one end, put a piece of foil. Okay. On the other end, put a piece of wax paper.
Mm-hmm.
All right. Take like a push pin or a needle, and you're going to create a small hole. Now, you need to go outside because you need the really bright light.
Yeah.
I've used like a stop sign, or you can use a garden sign. Now, you're going to put the pinhole side towards your garden object, and you're going to move it around. And that's why I say use a piece of wax paper, because ultimately you're going to see the image of that. It's going to be fuzzy. It's not going to be crisp, but you're going to see the image on that wax paper.
Okay.
Of what you're looking at. So that gives you an idea. Now, if you're doing it with a shoebox, you're going to do the same thing, except you're going to put a piece of white paper on the back, and then you can cut a hole next to the hole that you use for your pinhole, and you can put your camera phone right up there next to it and take a picture of what's projected on the back of the shoebox.
Okay, that makes more sense. Okay.
Yeah.
I can handle that. I was making it into
now
something
the other thing is you can even do and we use actually pinholes to do eclipses, to watch the solar eclipse, because you just take a piece of cardboard and you use the concrete as your screen, and then you can take a picture of whatever's coming through onto the concrete.
Huh. Okay. I can
Yeah.
handle this.
No, people try to make it a lot more complicated than it is. A pinhole is really, I mean, you can take little kids out and do pinholes with your hands, you know, on the
Uh-huh.
concrete. It really, the thing I also think that people think about is that they're going to get a really sharp image, and you don't. You get a
Okay.
fuzzy image.
Okay. I can handle that. I
Yeah,
can do that. All righty. Well, thank you so much, and I hope you have a good rest of your day.
you too.
Talk to you soon.
All right, bye.
Bye.